So, I hope the sound is working well. Let's speak a little bit now about the assignment that I think would be useful for you to do. And as I said, what we would like to do is make a, say, software controller. So we have some kind of device. Could be this ASML machine. I don't like this pen. So an ASML wafer scanner. And what I would like to ask from you is make, it should not be too big, smaller is always better. It doesn't have to be ultra realistic, but because we have to learn it, the language, we have to learn the tools, we have to get acquainted with all these sort of strange quirks, etc. So we need a little bit of time. So make it rather simple, but I at least would like you to make a system with, well, at least 2, preferably 3 parallel components in it that completely controls the relevant part of this desired component at hand. ASML wafer stepper I will use as an example. If you believe that you would like to do something else, or even if you think it would be much better so you have an interest in a particular way of a particular theory or something like that, and you would rather like to do that, then we can also see whether that would be possible. Well, I had this group of students, and they came to me. These were very well, students with their own mind, and they said, well, recently our lizards died in this lizard box, and that was due to the fact that the heating was too hot. It just cooked the lizard alive, which we don't want to have again, and therefore we want to make a controller for the heating of the lizard box with redundant sensors, etc. And they did do that, and actually they were quite good students making rather nice models. Well, if you have some, well, it doesn't have to be about lizards, of course, but if you have something else in mind that you like to do yourself, simply because then I would be quite happy. Well, I think we should discuss this a little bit, but I think we should try and do that. Anyhow, if we have the wafer stepper, so what is the wafer stepper? I already had this picture. This is a device. Let's make it simple with 2 locks here. This is a chamber that works in vacuum. And we already saw this. Here we have this ultraviolet light source, this extremely expensive lens made by the company Zeiss. I think Zeiss is, well, they used to make photo cameras, but now that everybody has an iPhone, the whole market for camera lenses collapses, and this is one of their main markets now. So this is a big lens. Here, you can put a wafer. Here you have a measuring position. There is a robot moving the wafers back and forth. There is here a staging position. There's a robot here. So this is a robot. So maybe I should draw it like this. So this is a robot moving the wafers from these positions back and forth. You can use both sluices here. So here we have a door, here we have a door, there's a door, there's a door, there's a robot here, and there is a stack of wafers here, and this robot simply picks out a wafer. Then the door should be open, so your control system, well, should first instruct the robot. Then, of course, we should take care that the door is open, otherwise it will bump into the door, which is not allowed, so the door should be open. Then there is this position where you can put a wafer here. Then you should close this door, open that door, and the wafer is moved in. And the controller simply gives instructions to the robots to do that, and it gets information back on the status. Because it could, of course, be that this door gets stuck. So it doesn't open for some reason. So in 99.99% it does open, but sometimes it gets stuck. Then, of course, this robot should not be instructed to use that. So you see information flows into this direction and into the other direction. So how do we go about this? What is extremely important, so Mohammed already showed you this picture with different components and the fact that you don't want to look inside. What's inside there is how different components, so this component, how this communicates with that component, and that component, how information flows in here, is generally quite non-important. What is extremely important for such a system are the external actions. So the commands that we give to these physical systems, the information that we get from this physical system. Well, it might also be that we provide information to the system to actually start working, and it might be that we have feedback here. And these are called the external actions. And the first thing that we should do is sit down and simply think about what are the external actions of our controller. And we typically can write them down as well, for instance, there could be this action open. And I generally find it extremely useful for the students that, and I instruct them to do it. They write open as the name of the action, and then simply give an explanation, a short explanation, what it means to open. It means this is the instruction to this particular door. So there might be an identifier of the door behind it. So this is an identifier of type identifier. We will come to how to specify that. It's very straightforward. And then this means this is an instruction to open the door with the identifier ID. And so we make a list and we get already a good feeling about what the system is doing. There can be an information floating back, namely is open. And there could be an identifier and a Boolean B. This is how I write the type of Booleans with an open B. And this means door, the door with the identifier ID just indicated that if B is true, the door was open, and if B is false, the door was closed. Well, try and sit down and simply identify all these actions. It's quite doable, but it is quite tricky because all of a sudden if you do that, and I'm quite in favor if you do, you can do the assignment alone, but also in pairs, you already get a discussion. Should we do it like this, or should we send a different kind of message? What is the information that should be in this message? Determining that this is part of the initial design of the system. Then the second step is to write down the requirements on this behavior, just in words. So we will go to logic, and we will be able, so we will, Mohammed will present the modal mu calculus. That is sufficiently strong to put every requirement that you can think of into modal formulas and check it. But what is quite tricky is to define the requirements on the behavior, and you should formulate this in natural language. So write down the requirements on the external actions. And, well, one of my experiences is if you do not quite know how to write down such requirements, then it might be extremely hard. Actually, I once sat with the people of the Dutch Railway Company, and they said, well, I want to write down the requirements on these safety systems to know what they actually guarantee, and they said then you should speak with our top engineers of the Dutch railway company regarding safety. And we sat there on the table, and I said, well, my first question was, I want to write down, to have the requirements, can I get the safety book of the Dutch railway company? Because you are so professional and you are so safe, you have this book, you can give this to me. And then they said, yeah, maybe we should tell you something about the Dutch railway company. We do not have such a book. Our systems work fine. And that was by and large the case, but when we started to verify. But we did not never explicitly write down what safety means. And I was quite shocked, not at the level of software. They have very stringent requirements on the strength of the iron and other, but not on software. And then I said, well, okay, let's then define them together. This is the safety box. What does this safety box guarantee? So, well, you are the experts, you should know. And then they were sitting there and saying, wow, yeah. That is difficult. Well, I think we know the answer. Trains should not collide and trains should not derail. And I immediately said, no, that cannot be true. And they were, well, we see trains collide all the time. We call that coupling of trains. That is a habit of trains. No collisions is not what this software guarantees, because it can actually happen. And then they said, well, yeah, you have right. I said something similar about derail. And they said, yeah, trains can collide. Well, then we do not, then we have no idea what actually these safety boxes are guaranteeing. And what was the actual problem? Because then we sat down and we defined all these requirements. And when that happened, they said, oh, you can actually, you really have 99% of all the requirements that we have. So we sat down, let's do it for the example of the railway. You had the railroad, and we said, if there is a signal showing green in this direction, then of course the signal in this direction should not show green at the same time on a single track. And they said, of course, that's a requirement. If you have a switch that moves, gets the instruction to move, then there cannot be a train in the neighborhood, otherwise we would have a derailment. And that is what this system guarantees. And they said, yes, of course. And this is the kind of properties that I am actually looking for. Namely, properties that are very simple to understand, but which are actually the essential properties that the communication here should satisfy. Now, let's go to this particular system with these doors, with the vacuum here. What would be a requirement on this particular system? That the software, the control system here, should really guarantee. Do you have an idea? Well,
the wafer on the laser.
Sorry,
The wafer should be under the laser.
Yeah. So this. At some point, what we want to have is that a wafer being here will move inside, will have been put under the laser, and will be moved out again. So if we get the indication here that the tray of tracers has been processed, all the wafers should have been processed. I think that is a very valid requirement. So it should go there and it should go there. A very simple one. This is vacuum. And we have a sluice complex here. So what is it that we should never allow the software to do? Yeah, exactly. So we have a door here and a door here. If we both open them, then we hear a loud bang, and this expensive lens will be destroyed. They can throw it out. It cannot stand air, at least not for longer than 5 minutes or something like that. So that's one of those things that should never ever happen. These doors should never open at the same time. So, in terms of this interface, we can only speak in terms of actions because our world is here, this is just the physical world. We say, if we instruct this particular door to open, we had received a message that this door is closed, and in the meantime we did not instruct this door to open, so we are sure that it is really closed. And this kind of rather unpleasant phrases are the requirements to write down. Another one, this robot, if we instruct this robot to move a particular wafer from here to there, then we know that this door is open. So the last message we received about the status of this door was that it was open, and we did not instruct it to close in the meantime. If you sit down and all of a sudden there are far more requirements than you initially would think of, but I always restrict the students to 10, 12, because otherwise there are too many, but you can easily write down sometimes 100. This robot should not put a wafer there if there is already a wafer there. Well, these kinds of very elementary properties, these are the safety properties, are important, and you have these liveness properties. Ultimately, this tray of wafers, after we get the start message, there will be the message that the whole tray is actually processed. So, when we get the start message, eventually the ready message will come. And if the ready message comes, all the wafers have been processed properly. Well, for the realistic system, there are all kinds of scenarios where all these things get stuck and it is getting really complex. Here, we should probably assume that everything works fine. All the robots work fine. There are no further complications. Well, the realistic systems, sometimes I ask myself why, but it's utterly more complex than this. But let's restrict to that. So we write down the requirements, and we write it down in natural language. So, plain English is would absolutely do. This is also because we can communicate this. If we do it in formal logic, then our potential customers for which we are working will not actually understand what the requirements are, and I think it's very good to show them the actual requirements. Now, third thing to do, and I would like to assign a small slot this evening where you can work on these things, so this is all without the tools, is sit down and determine what your architecture would be. So if you would divide this controller in 3 components, what is the responsibility of that component, what's the responsibility of that component and that component. It is utterly important that the tasks of these components are very well defined. It helps you to control the whole system. If you make the software architecture in a mess, then formal modeling will not help you at all. So we will not actually have formalisms to verify whether this is good or not good. Actually, software architecture is not in a state where you can say, this is the way to make a good software architecture and this is the way to make a wrong software architecture. There are some rules that you can adhere to, but it's more an art still than a science. But typically write down what the software architecture is. Write the software architecture down, including responsibilities of each component. So the responsibilities of all the components and the interactions, how they communicate internally. So they simply also communicate with actions, so we can name these actions. Later on, we will hide the actions, so we will speak about the internal actions, that is why internal actions, but we will not see it in the external behavior. We will not use these internal actions to check. We check the properties only at the external behavior, but we still can have that this particular system gets a message that the door is closed, and that it sends a message to this component and to that component that the door is actually, that a particular door is closed, such that it can send this message to open another door. So that is a sequence. So including responsibilities and internal actions. And that basically defines the structure. And up till now, we did not see any MCRO tool to use. This is just a piece of text. Now MCRO2 comes into play, because we now know exactly what the responsibilities of these components are. If we take this component in isolation, we know how it communicates here, how it communicates to the outside world, how it communicates here. So we can now simply write down the behavior in MCRO2. So, fourth step, define behavior in MCRO2. And then first we write down the behavior of these individual components. After that, we simply put all these components in parallel, define how they communicate, and we have the behavior of this whole system. And we can ask the tool to generate this behavior, and we can try to reduce it modulo by simulation or trace equivalence and look at the results. If you do trace equivalence, then generally you will find it painful. By simulation is technically much more convenient, but we could try to do that. And then we have basically the whole behavior. And if you come to me and you say, I have a large system with 10,000 states, then I will grin a little bit and say, well, 10,000 states is still small. If you would come to me with 10 billion states, then we have somewhat of a problem. But everything up till 10 million states, well, we have a 1 terabyte main memory computer in Eindhoven, there 1 billion states would work, is not a problem at all. So 10,000, 100,000, 1 million states, it's typically the size that I expect here, but it's already far too big to actually inspect. Just inspect the transition system by itself. Okay, then we have the behavior. And then, and this requires some skill in logic, we will take the requirements here and translate the requirements, translate and verify. So translate the requirements to the model mu calculus and verify them. And I would be quite amazed if somebody would come to me and would say, it turned out that we had a model, and it turned out, because this never happens, we have all the requirements, we check it on the behavior, and it was all correct. So what happens if that all of a sudden you start to realize that a requirement is not valid, that this is due to a misconception or a stupid error or whatever problem in your model, and you will actually have to adapt your model. Or it can be that you look at the requirement and that the requirement actually is not true at all. So you said that under all circumstances everything which went in should go out, but all of a sudden you start to realize and understand this behavior, that is an unnatural requirement, that is actually, you did not think of this particular scenario where that was not the case, and now you have detected that. So it can be that you actually start to adapt the requirements in this part, sometimes you start to realize that your software architecture was not correct. So from this point on, we will make jumps back and forth until we have all the requirements in such a way that we can verify them and that we are satisfied with it. And then we have the design of our behavior, and we could give this design to a programmer that can read, of course, MCRL2, and he could simply go rule by rule and put it in a program. This AES Verum company has translators that would automatically translate this to code. We do not have these translators, so if you have a specification in MCRL2, then you really have to provide the translation by hand, but I think that's only useful. Because that is yet another check on the quality, and the quality of the code is far more important than the speed of operation. But basically, we then have the proper model, which at least for sure satisfies these requirements, and hopefully we had all relevant requirements. So we have this model of high quality for the next steps to be programmed. And then, of course, I will ask my own students to write a report, and we discuss the report, and they should provide all the proofs and all the models in there. But that is something we could skip here unless Mohammed thinks otherwise. So we do not have the time to write complete proper reports. I think we should come into the situation where you can actually have the translated requirements and can actually verify. So you should basically go through these 5 steps. And I propose to start with this at the end of today. Okay. Questions?
I missed the mouse because it can be a little bit distracting when I click on. Oh yeah, here. Yep. Very good. So, are we ready? Has anyone left or no? Okay, we go on. So, if you remember from the last lecture, we were interested in the notion of behavioral equivalence that allows us to compare different models. And what was very important for us was to be able to basically abstract from what is happening inside the system, right? So internal actions should be invisible to the outside world. That's what we want to achieve in this lecture. And for that, we introduce one action called tau, which is representative of all internal actions that we do not want to expose to the outside world. Okay? So if we have such a system where some actions happen internally, there are details of the implementation, there is an operator in MCRL2 that allows you to rename all of them into tau. Okay? So you specify your implementation with lots of details. After you're done with it, you have inspected it, you're fine, you want to now analyze it, you rename everything that is internal, that is not at the outside border of your system, into tau. And then there is a notion of equivalence that allows you to compare 2 systems such that one of them contains a lot of taus and the other one maybe fewer or none. So fewer taus or no tau at all. And thereby you can establish whether your implementation is correct with respect to the higher level. So the implementation is correct with respect to the higher level specification or not, right? Right, so we want to come up with notions of equivalence that basically neglect those internal actions, those tau actions. Is the idea clear? So here is the first attempt where we take the notion of trace equivalence, the very weak notion that we saw earlier today, and we adapt it such that it jumps over the taus, basically. So it neglects the taus by jumping over them. So you remember this was trace equivalence. The set of traces of a state are defined as follows. Empty trace is always in the set of traces of any state. Oops. Termination is in the set of traces if the state is terminating. And then if the state affords an outgoing A transition to T prime, and then the target state affords a trace sigma, then you concatenate them and you obtain A sigma as a trace of T. You remember that, right? Now what we add to it is, first of all, we allow to jump over. So this remains the same. If the outgoing step is not a tau, then you basically apply the same rule as before. I'm defining weak traces of a state, okay? So the first 3 rules are the same, except for that I only apply this rule if A is not tau. Okay? But if A is tau, I basically jump over this transition and I look at the traces of T prime and then take sigma as the weak traces of T. Right? So I'm interested in traces of T. If T affords a tau transition, I basically jump over the tau, look at the emanating traces from T prime, and put them as the weak traces of T. Is this clear? Yes? No? Yes? Yes? Good. And like before, I say so this is a mistake. Two states are equivalent if their set of weak traces are equivalent. Are these two systems weak trace equivalent or not? Let's take 15 seconds and then come up with an answer. Who thinks they are? Who thinks they are not? Okay, so many people are undecided. Let's look at, so this was our definition, right? We want to calculate the set of traces, weak traces of S naught and also T naught. For S naught, it's quite simple because there are no taus. Basically, it's the same as strong traces, right? If there are no taus, you basically apply the same rules as before and you obtain the weak traces. So there is nothing to check, right? But this is more interesting, so let's see how it works. For these two, they do not afford any taus. So basically, their only traces are the empty trace and the tick, the termination, right? Because there are no taus, only the old rules apply. And in this case, you have epsilon and tick. You agree, right? We take another step back. Again, there is nothing much to check because in these cases, there are no tau outgoing transitions. You get epsilon, coffee tick, and that's it. And likewise, in the other case, you get epsilon, T, and T tick. Right? Yes? Now this is the interesting case. T1 affords two outgoing tau transitions, right? If you take this one, the rule here tells us you could jump over this tau, right? And then take the outgoing traces of T2, and those become the weak traces of T1, right? So we did calculate them before, right? So we knew that traces of T2 were empty, coffee, and coffee tick. In this case, we had empty T and T tick. We could jump over these two taus, and thereby we obtain epsilon, coffee, T, coffee tick, TT as weak traces of T1. You agree? Then for this case, it's quite simple because there is no outgoing tau transition. You basically concatenate coin with what you had before, and then you obtain this one. Right? And if you remember from this morning, this was exactly the set of weak traces in this case, there are no weak traces, of S naught. These two are weak trace equivalent. But do you think these two should intuitively be equivalent or not? So intuitively, if you are given this as an implementation of this specification. Yeah, the question was, what was my question? So I'm explaining the question again. If you are given this implementation of this specification, would you consider this a correct implementation or not? Is there anyone who wants to argue why this is not a good implementation? Why T naught is not a good implementation of S naught?
The left transition system, we have a choice in S1.
Right. So here you can always choose between coffee and tea. That's true.
But in the right transition system, we can't have a choice between coffee and tea.
Well, you kind of have a choice if you're here because the system may do something internal. It may make some sound, something that you do not observe really, and then it will offer you coffee or tea. So you basically have some choice if you're here. It can offer you coffee from here. It can also offer you tea because you don't see this, right? This happens internally. There is an internal clock And then
User cannot specify its choice.
maybe there is a slight. So I think you're getting at the right answer, but not quite. So take, for example, yes, you want to say?
The environment has no control over the.
That's true. The environment cannot decide about the tiles, but as long as you're here, you still have a choice, right? As long as you haven't moved on, the system does offer you eventually in the future both coffee and tea. But the problem is, assume that the system decides by itself to take this tile. You have no control. This is an internal action, right? As soon as you go here, you end up in a state where you cannot get tea anymore, right? So by doing something internal that you cannot observe, the system evolves into a state in which the T option is removed automatically. And this is a very bad decision. This is a very bad internal decision by which you are deprived of your choice, basically. Yeah, you had a choice here always, while here the system can evolve on its own into a state in which one of the choices is removed. And that's why this is not a good implementation. That's why weak trace equivalence is too coarse. We should basically go to the other side of the spectrum and search for something that preserves the moment of choice, basically. Is this clear? Shall we go on? Right, so the first idea is called something weak by simulation. Unfortunately, this is not exactly what one wants to have. Of course, it's arguable. But we'll start with that, and then I will present you a slight variant of that called branching by simulation, which is slightly better than weak by simulation. They're very close to each other, but branching is slightly better. And I'll show you why it's slightly better. Intuitively, it makes a little bit more sense. Now, the idea is very simple. On one side, you can do an A transition. On the other side, you're allowed to mimic that by doing a number of internal actions, 0 or more, and then doing an A, an observable A that matches the A on this side, and then 0 or more tau actions again. And then the targets should be again related. Note that I don't have any requirement on the state that I visit in the meanwhile. So if I do an A here, I can do a number of internal steps that are not visible, and then do a visible A step, and then a number of internal steps, but the targets should be again related, right? I do not have any requirement about the states that I visited in the meanwhile, right? That's the essence of weak by simulation. And if one side can do a tau transition, the other side can mimic it by either doing another tau transition or doing nothing. Doing tau transition is actually covered already here, so doing nothing is the only addition, basically, right? If I do an internal action, I can do nothing because that's not observable. So this is by simulation as we knew it from the past. If you pick two related states, if S can make a transition, T should be able to mimic it to T primed. Now we extend it by two different rules. One is that either this A is a tau, then T is allowed to stay there, do nothing basically. If you do a tau here, you do not have to evolve at all. You can stay in the same state where you were before. Right? And likewise, if this is not tau, then you can do a number of taus, and then do an A, and then a number of taus, and then the targets should be related. That's the formal definition of weak by simulation. And there is a slight modification for termination, which I've omitted, but that's not very important. Oh yeah, no, it's here. I haven't omitted. If S terminates, then T can do 0 or more tau transitions leading to termination. That's also the slight modification. Is this clear? Now let's. So this is a diagrammatic representation of the same thing. If one side does an A, the other side can do a number of taus, 0 or more, followed by an A, followed by a number of taus. If one side does a tau, the other one can stay the same place, and still the source and the target should be related. Now there is a slight variant called branching by simulation, and then I will try to motivate that, which not only requires you to mimic the source and the target state, but also all the states that are visited in between. Okay? So basically, if you do a number of taus before you do an A, the source states before doing an A should be related to the source, and the target should be related to the target. This has some more intuitive properties, namely it kind of preserves the structure of your transition system. I think I have an example on the slide, otherwise I could do another example on the board later on. The last notion that I would like to introduce, and then maybe we do some exercises on the board, is something called rootedness condition. So take these two systems. Are these two branching or weak equivalent? Rooted I haven't explained, but weak and branching, in weak bisimulation, I allow to do a number of taus followed by a number of taus, but I have no constraint on the state that I visit in the meanwhile. Right? In branching, I require that the state right before A is related to the source, and after A is related to target. So basically, I'm cutting this into two pieces, and I require these to be related before the A and after the A. Actually, it's equivalent to the definition which this is preserved, and then this should be preserved, but that's not important, right? Is this clear now? Yeah. Now the question is whether these two systems are weak and branching equivalent or not. Branching bisimulation equivalent. They are not. They are equivalent. Yeah, so here you can do a coffee. The only way for this one to do a coffee is to do a tau followed by coffee, which is fine, right? If you look at weak, you only require these two to be related and these to be related. And that's trivial. I've already checked that all outgoing transitions can be matched, on this side at least, and the targets are related because they only afford termination, right? On the other side, this can do a tau. This can mimic a tau by either doing nothing or by doing another tau, right? And this one can choose to do nothing and stay at T naught. T naught and S1 should be related, but they're identical, so they are also equivalent. Is this clear? If not, I can draw it here. Does anyone want me to draw the bisimulation relation there? Maybe? Yes? Anyone? Yes? So I guess I can erase this one, right? So here is S naught, the initial state. Right? So for these two to be, we first check weak, okay? And branching is very, very similar. For these two to be weak bisimilar, the initial states should be related. So there should be a relation R that relates the initial states, right? I take a coffee on this side. The only way for this one to mimic the coffee is to do a tau followed by coffee, right? And the bisimulation transfer condition requires me to relate these two, right? In order for these two to be related, if one affords a transition, the other one should be able to mimic it weakly by doing a number of taus followed by that transition, but that's not the case. If one terminates, the other one should weakly terminate, but this also strongly terminates, so this is fine, right? These two are related. I've checked this transition, this is checked. I need to check this one. I haven't checked this one yet, right? This one does a tau. How can this one mimic it? How can T naught mimic it? This one does a tau transition. Look at the definition. If A is tau, there are two options. Either you can stay in the same state, or you can mimic the tau, right? So this one does a tau. This one can mimic it by staying in the same state, and thereby these two should be related using the same relation, right? But these two are related using a weak bisimulation relation. Why? Because they are just identical. They afford the exact same transition system. Is this clear? So there is nothing to check about this new pair. So this is a weak bisimulation relation, and it satisfies all the conditions that are specified there. In particular, it relates the initial states, and hence these two are weakly bisimilar. Is this clear? I would argue this is also a branching bisimulation relation, because branching tells us if you do a coffee here, you not only should be able to do a weak coffee there, but also the state right before doing the coffee should be related to the state before doing coffee over there. And that's already the case. So this is both a weak bisimulation relation and a branching bisimulation relation. Any questions? Everyone agrees? Now, these two are weak and branching bisimilar. Remember, we required our notion of behavioral equivalence to be a congruence. What would congruence mean? One by one, what do you say?
Preserving behavior in the context.
And what you said? The same answer? Okay. So we want two equivalent systems to behave the same if we put them under any context, basically, right? And one particular context is adding a T feature, for example. I take this machine, I just add a T feature to it by taking non-deterministic choice with T, right? Alternative choice with T. So I add T option to this one, and I add T option to that one. I should obtain the same machines again, right? I haven't done anything to the coffee part. I just added one T transition. Are these two weak or branching bisimilar or not? Choice is not good. Okay, so assume that they were bisimilar. Okay, this one can do a tau. What are the options for this one to mimic it? Either it should stay in the same state. Can I draw here? Can I draw here? Do you think? I will do it here. So I take the same transition system. I add T options to the two sides. So this one can do a T. Let's call this S3. It doesn't matter. The name of states do not matter, right? We decided we are doing action-based, so what is in the state is immaterial here. T, T2, right? This one can do a tau. There are two options for this one to mimic it. Either it should do a tau. It cannot, right? So the only option for this one to mimic this tau is to stay in the same state, right? So if these two were bisimilar, weak or branching, these two should also be bisimilar, right? If the initial states were bisimilar, this one does a tau, so this one should be able to mimic it. It cannot do a tau. The only possibility for this one to mimic it is to stay in the same state. Thereby, S1 and T0 should be weak or branching bisimilar, depending on which one you start with. But this one cannot be weak or branching bisimilar. Why? Because this one affords a T transition. There is no way for this one to mimic the T transition. So these two cannot be bisimilar, thereby these two cannot be bisimilar. Right? So neither weak nor rooted are preserved under non-deterministic choice, under an alternative choice. So they are not a congruence as we discussed it, right? So we need to amend them a little bit, and the only amendment that we need is so weak and branching are not preserved under choice. That's basic. That's the bottom line of this example. Now the basic idea is something called a root condition. It was also discovered by Rob van Glabeek and someone else, Bloom, right? Was it Bloom and Van Drager came? Bloom, no, Weiland and Van Glabeek came with the.
Already came up with rooted weak bisimulation.
And then.
And Van Glabeek
and Weiland, yeah.
Already defined rooted.
So they have a paper. These two people, Weiland. Is it correctly spelled?
Yeah,
I think so. And Van Glabeek have a paper, I think in Journal of the ACM, if I remember well, about this root condition. And it's a nicely written paper, whereby they state, in order to fix this problem, you require the first tau transition, the first tau transition to be mimicked exactly by another tau transition. You're not allowed to stay in the same state. So only from the initial state. If one side can do a tau transition, the other side should mimic that tau transition with another tau transition. It cannot stay. If that is satisfied, then the rest remains the same, and then this rooted branching bisimulation is a congruence for the operators that you have seen today. right? So the only modification is that the first transition should be exactly mimicked as in a strong bisimulation. The rest can be mimicked using the rules of rooted or weak bisimulation. Is the idea clear? So in particular, these two systems are not rooted branching bisimilar or rooted weak bisimilar, because this one can do a tau. This one should be able to mimic it exactly with another tau, not by staying in the same state, and it cannot. So these cannot be related using rooted version of these equivalences. Yeah, I see some of you are a little bit puzzled, but okay, it's a little bit of a complex concept. I think, given the time, how am I doing? So what time should we stop? I can do a few examples if you have time.
Ik denk dat een aantal examples.
Ja. Voorbeelden. Doen we. So let's do a few examples. We start with bisimulation because it's a very interesting notion. I go back to a strong bisimulation, okay? So not weak, not branching, just simple, plain bisimulation. Oh, I don't like red. This is a little bit more complex, so take your time, spend a minute at least looking at it, and then if you know an answer, just raise your hand, we can discuss it. And it goes on like this. So for each n, it's infinitely branching, countably infinitely branching. For each n, you have one such thing. You do n number of a's in a row. Okay? So Sn2, Sn3. It goes on up to Snn, basically. And there are omega number of those, okay? So there are infinitely many of those. Another one, okay, this might be simple to start with. Another one just does an unboundedly many a's. Are these two bisimilar or not? Before that, are these two trace equivalent or not? Are these two transition systems trace equivalent or not? Let's first solve that. So let's call this T0, just to avoid any confusion. Is S0 trace equivalent to T0 or not? No, there is no termination here. There is no termination. So this one only deadlocks here. There is no termination. So basically, this one can do 0 or more unboundedly many a's. This one the same, right? So the set of traces for this one is basically empty, A, etc., and unboundedly many a's, right? You could write it down basically as A star. This is the language of traces of this one. For this one, it's the same, right? It can do empty trace, 1A, 2A's, 3A's, as many. So they are indeed trace equivalent, right? Are they bisimilar or not? Wait for a few seconds. Does everyone agree why they are not bisimilar? Does everyone agree that they are not bisimilar before we discuss the reason? They are not, you say. Does anyone think they are? No. Can someone explain why they are not? You said they are not. Why they are not? Okay, so let's.
Say any of the S states in right part can have any number of A.
Hmm.
Then any of them is not related to T.
Okay, I think you're getting at the core reason. So assume that they were bisimilar, then there should have been a relation relating the initial states, right? Let's pick the one that forces the other one to pick its only choice. So, for example, pick this one, okay? This one can do an A, right? The other side has only one choice to mimic the A, namely by staying at the same state. Thereby, these should be related using the same relation. But that already fails, because that one affords an outgoing A transition. Note that I'm switching the sides. I can switch. I can decide which side I'm playing at each point of time. I started by playing on this side. I concluded these two should be related, T0 and S1. Now I switch my side. I play on this side. I say, this one can do an A. Show me how you can mimic your A here. It cannot do it, so this one fails. Thereby this one fails. Is this clear? Now let me change the game a little bit, change the question a little bit. Slightly more interesting. So I keep S0 intact. I do not change it. Oops. But I change T0 by being the same copy as S0. So it includes a copy of S0, but in addition, it has one more state. Let's call this S omega. Okay? Let's call this T so that it doesn't clash in names. All right? So there is an exact copy of S0 in T0. But it has one additional transition, namely it goes to T omega and it stays there. Are these two bisimilar or not? So if you say they are, you should show me bisimilation relation. If you say they are not, then you should give me an argument why there exists no bisimilation relation. Who wants to try that first?
They're not. Because if the right system takes the T omega,
Okay,
and the left system tries to mimic that transition.
that's good, right?
By going to the state SI1, for example.
That's a very good argument. So let's go step by step. So you're saying this one can do an A step. This one has to mimic it to some other target state, right? It has many choices. Choose an arbitrary one. It doesn't matter which one you choose, right? I don't assume anything, but that there should be an A transition to some SI1, right? With I number of A's, outgoing A's, going to SII, right? I don't assume, I don't have any presumption about why I is, but there should be some I, right? That's what your argument. So the target of this one should be related to SI1, right? Assume that these two were bisimilar, then the targets should be related, namely these two should also be bisimilar, right?
But the left system can take at most IAs, while the right system can take 3.
Yeah, so it became a little bit hand-waving now, so it's not a formal argument. But he's saying this one can afford at most IA transitions in a row, I minus 1, right? While this one can afford I and more, unboundedly many transitions, right? So there will be, if you keep on with the same argument, these two should still be related, right? Again, this is a little bit of an informal argument. You could take it into an inductive argument, right? But then these two should be related. And then that fails because this does not afford any outgoing A transition, while this one still affords another A. Is this clear? So this can be formalized as an inductive argument, right? So you should show that there is no such SI1 by induction. It cannot be S1, it cannot be S2. If it's not Sn, it cannot be Sn plus 1 either, right? Is this clear? Okay, one more last example about biosimulation. Maybe if we get some time, I will do some other examples about weekend branching. Because weekend branching need really thinking. Also from my side to cook up a good example. The question is whether S naught is strongly bisimilar to T naught or not. First of all, are they trace equivalent or not? S naught and T naught, are they trace equivalent or not? They are trace equivalent, right? They afford empty A, AD, AB, AC, and AE, right? Both of them. So they are trace equivalent. Are they bisimilar or not? Take your time. Take your time. Is there anyone who thinks they are? No? Okay, who said they are not? Who wants to? Yeah, let's try. Why are they not? No, wait. I am not at S11. I'm at S naught. So first of all, they should be related using some relation R. Otherwise, there is no game to play, right? Now, what game do you want to play? Which A transition? Okay, so S naught can do an A to S on 1, right? Right. So on this side, we can do an A transition. This one should be able to mimic it. And he's saying we have two choices here. Either we take this one or we take that one. So there are two possible candidates for the biosimulation relation. So we could have that these two are related. Let's call this R naught, right? Or these two are related. So there are two candidate biosimulation relations that may work here. Yeah? We are. No, you don't have a choice, right? You can choose your own move. The other system can make its own move. It's a game, right? You can only decide about your own move. This guy has its own move. So it can decide either it goes here. Oh, right. Sorry, I was explaining the wrong thing. You're right. So you're right. Yeah, either S11 is related to T11 or to T21. You're right. Okay? Now, what happens? I'm not following you here. So you should show that neither of these two can be a biosimulation relation. How do you do that? Why R naught cannot be a biosimulation relation? Well, it's not about choice, right? Assume that these two verbi similar, right? This one can do a C. Show me on the other side how you can mimic the C. That's not possible, right? T11 can do a C. S11 does not afford an outgoing C transition to mimic it. So R0 cannot be a bisimulation relation, right? These two can never be related because T11 affords a C. This one does not afford a C. Right? So this one fails. Yeah? Likewise, T21 and S11 cannot be related because S11 affords a D, T21 does not afford a D. So R1 cannot be a bisimulation relation either, thereby R cannot be a bisimulation relation. Yeah? So you show that both the strategies of the opponent fail. That's why there is no winning strategy over your choice. Yeah? Good. So I think we can park it here. We are, I think, accurately on time now. Okay. But I think it's a good point to take a break. So we take now half an hour break, and then we come back at 3:30.